Hello, and a very warm welcome to the Sleepy Scientist. I'm so glad you're here tonight. Together we're going to wander into one of the strangest, most wonderful claims in all of physics. That a single quantum particle can be in two places at once. First though, a brief and honest word. You've probably noticed there are no ads on these videos, so nothing will break the quiet tonight. Keeping it that way does take a little help though, and the best way to lend it is the ebook. If you have a spare minute, and only if you do, pause here and take a look. There's a QR code on screen throughout, and a link down in the description across to the website, thesleepyscientist.com. It's an unhurried, patient guide to quantum physics. The ideas behind these videos given a little more room to breathe, with the full narrated audiobook alongside. Honestly, a quiet look really is the most helpful thing you can do to keep these videos coming. That's all I'll ask tonight, and I ask it warmly. Thank you. Now before we begin, let me know where in the world you're listening from, and what time it is for you. I always enjoy seeing how far these quiet little journeys travel, while the rest of the world is busy pretending to be sensible. It's a claim that really should come with a small warning label. In ordinary life, things simply aren't allowed to behave this way. A cup is on the table or it isn't. A planet is on one side of its orbit or the other. You're either in bed listening to this or somewhere else insisting you aren't tired yet. But at the smallest scales, reality follows different rules. Electrons, photons and atoms can be described by states that hold more than one possible position or path at once before anything is measured. They aren't tiny balls hiding in one secret place. Their possibilities can spread, overlap, and interfere, and when we look carefully enough, those possibilities leave real patterns behind in real experiments. So tonight we'll move gently from the familiar world of ordinary objects into the stranger world of matter waves, superposition, and the double-slit experiment, and towards the delicate reason this weirdness usually disappears long before it reaches the scale of cups, chairs, cats, and people. So get comfortable, let the day soften a little around the edges, and picture a single tiny particle moving towards two possible paths. In the world we know, it should choose one. In the quantum world, that assumption is exactly where the mystery begins. In ordinary life, being in one place at a time feels less like a scientific rule and more like common sense. A cup sits on a table. A chair rests in the corner. A person cannot walk through one doorway while also walking through another doorway on the opposite side of the room, unless something has gone very wrong with the doorway, the person, or the story being told. This is the world our senses are built for. It is a world of definite locations, solid objects, steady surfaces, and paths that can be traced from one moment to the next. If a football crosses a field, it does not blur into every possible route at once. It follows a path. If a stone falls from a cliff, it does not explore a polite selection of alternative cliffs on the way down. It falls in one direction, under gravity, with a motion that can be described extremely well. For centuries, this was the heart of physics. Isaac Newton gave the world a deep and powerful description of motion. In Newton's classical mechanics, an object has a position, it has a velocity, it has a mass. Forces act on it, and those forces change its motion. If enough information is known about the object and the forces around it, its future path can be predicted. This picture is not wrong in the world where it belongs. It is one of the most successful ideas in the history of science. Newton's laws describe falling apples, flying cannonballs, orbiting moons, tides, pendulums, bridges, engines, and spacecraft with remarkable accuracy. They are so good that even today, engineers and astronomers still use Newtonian physics whenever the speeds are not too close to the speed of light and the objects are not too small. In this classical picture, a particle is like a tiny object with a definite location. A grain of sand sits somewhere. A planet moves somewhere. Even if we do not know exactly where something is, classical physics assumes that the thing itself still has a definite position. The uncertainty belongs to us, not to nature. The object is not confused. We are. Imagine closing your eyes while someone places a coin under one of two cups. You do not know which cup hides the coin, but you naturally assume the coin is under one cup or the other. It is not truly under both. Your uncertainty is only a lack of information. Lift the cup and the answer is revealed. This feels obvious, and in everyday life it usually is. But the quantum world does not always behave like a hidden coin under a cup. At the scale of atoms, electrons, photons, and other tiny systems, the question of where something is becomes much more subtle. The particle is not always best described as a miniature ball sitting in one secret place, waiting for us to discover it. Instead, quantum theory describes it using a quantum state, and that state can spread across different possibilities. This is where ordinary intuition begins to wobble slightly. Not collapse dramatically, perhaps. Just wobble, like a table with one short leg in a quiet laboratory. The reason we do not normally notice this strangeness is scale. Everyday objects are enormous compared with quantum particles. A dust grain may seem tiny, but it contains an immense number of atoms. A bacterium is microscopic, yet it is still a vast structure compared with a single electron. A human body is not merely large by quantum standards. It is an entire weather system of molecules, heat, motion, light, electrical activity, and constant interaction with the surroundings. An electron is far smaller than an atom. An atom itself is roughly a 10 billionth of a meter across, depending on the atom and how it is measured. The nucleus at the center is roughly 100,000 times smaller than the atom as a whole. These sizes are so far below ordinary experience that our everyday mental pictures begin to fail. We can imagine tiny balls, tiny orbits, and tiny paths, but those pictures are borrowed from the large world. Nature is not required to use them. Large objects also interact constantly with their environments. A chair in a room is being struck by air molecules. It is absorbing and emitting thermal radiation. Light is bouncing from it into your eyes. Its atoms are vibrating. Its surface is exchanging information with the world around it all the time. These interactions make the chair behave in an overwhelmingly classical way. Its quantum possibilities are not absent at the deepest level, but they are hidden so thoroughly that the chair has no practical chance of showing up as a visible superposition in two different corners of the room. A quantum particle can be different because it can sometimes be isolated. A photon travelling through a carefully arranged experiment or an electron passing through a narrow opening can avoid enough environmental disturbance for its quantum nature to remain visible. Under those conditions, it may not behave like a little pellet flying along one fixed route. It may behave more like a spread-out possibility, one that can pass through more than one available path and later produce effects that reveal this strange shared history. This does not mean the particle becomes a ghost, a cloud of imagination, or a tiny indecisive traveller unable to read a map. It means that the classical idea of a particle as a small object with a definite position at every moment is incomplete. Quantum particles are described by rules that allow their possible positions to be distributed across space, and those possibilities can interfere with one another. That word, possible, needs care. In ordinary life, possibility often means ignorance. The keys might be in the kitchen or the bedroom because we have forgotten where we left them. The keys themselves are not doing quantum physics. They are simply waiting somewhere, probably in the least convenient place available. But in quantum mechanics, a particle's possible positions can be part of its physical description before measurement. The possibilities are not always just a list of what we do not know. They can shape what happens. This is why the claim that a quantum particle can be in two places at once is both powerful and easy to misunderstand. It does not mean an electron is a tiny marble duplicated into two separate copies. It does not mean a photon is sneaking around with a spare photon costume. It means that, before measurement, the quantum state of a particle can include more than one position or path at the same time. When those alternatives remain coherent, they can combine in ways that produce real experimental patterns. The large world teaches us that things are definite. The quantum world teaches us that definiteness is not always there in the way we expect. Between those two pictures lies one of the deepest shifts in the history of physics. The move from objects with fixed hidden properties to quantum systems described by states, probabilities, amplitudes, and measurement outcomes. So before asking how a particle can be in two places at once, it helps to see why ordinary objects cannot. They're too large, too warm, too complex, and too entangled with their surroundings. Their quantum behavior is washed into the familiar world of definite positions, but small, carefully isolated systems can preserve the delicate structure of quantum possibility. That is where the strange promise of the title begins, not with magic, not with confusion, but with the discovery that, at the smallest scales, reality does not always choose one clear path until the rules of quantum measurement force the question. At the end of the 19th century, physics seemed to be standing on very solid ground. The great laws of motion had been laid down by Isaac Newton. The theory of electromagnetism had been brought together by James Clerk Maxwell. Heat, pressure, light, sound, electricity, magnetism, and motion all seem to fit into a vast and elegant mechanical picture of the universe. It was tempting to imagine that nature had nearly been solved. Not completely, of course. Scientists are not usually allowed to say that without the universe immediately knocking something important off the shelf. But there was a feeling, at least among some physicists, that the main framework was already in place. The future of physics might simply involve measuring things more accurately, tidying up a few details, and perhaps finding somewhere sensible to store all the brass laboratory equipment. And yet, hidden inside those details were cracks. Not dramatic cracks at first, more like fine lines in glass. Small experimental puzzles that did not seem to fit the classical picture. When scientists looked closely at heat radiation, light, and atoms, the old rules began to strain. One of the most important puzzles involved something called blackbody radiation. A blackbody is an ideal object that absorbs all radiation falling on it and then emits radiation depending on its temperature. In real life, glowing metal gives a useful hint of the idea. Heat a piece of iron, and it first glows dull red. Heat it more, and the glow becomes brighter, shifting toward orange, yellow, and eventually white. The colour and intensity of the emitted light reveal something about the object's temperature. Classical physics tried to explain this glow by treating radiation as waves of energy that could vary continuously. The problem was that the prediction went badly wrong at short wavelengths. According to the classical calculation, a hot object should emit more and more energy at ultraviolet wavelengths, rising without limit. This failure became known as the ultraviolet catastrophe, which is a wonderfully dramatic name for a graph refusing to behave itself. In reality, hot objects do not pour out infinite ultraviolet energy. The world, quite politely, does not destroy itself every time someone lights a stove. Experiments showed a very specific curve for blackbody radiation, and classical physics could not reproduce it. In 1900, Max Planck found a way to match the observed data. His solution was strange. He proposed that energy was not emitted or absorbed in a perfectly smooth continuous flow, but in discrete packets. These packets were connected to the frequency of the radiation by a tiny constant. now called the Planck constant. Planck did not begin by trying to launch a revolution. He was trying to solve a technical problem in the physics of heat and radiation. But his idea contained something radical. It suggested that at the deepest level energy exchange might come in steps, not a flowing ramp but a staircase. The steps were incredibly small, so small that in everyday life they disappear into smoothness, but they were real enough to rescue the theory from disaster. This was one of the first signs that nature might not be continuous in the way classical physics had assumed. And once the first sign appeared, another soon followed. In 1905, Albert Einstein took Planck's idea further while studying the photoelectric effect. The photoelectric effect occurs when light shines on a metal surface and causes electrons to be emitted. Classical wave theory expected the energy of the emitted electrons to depend mainly on the brightness of the light. Brighter light should mean more energy delivered to the electrons, but experiments did not behave that way. Instead, the colour or frequency of the light was crucial. Below a certain frequency, no electrons were emitted at all, no matter how bright the light became. Above that frequency, electrons could be released, and increasing the brightness increased the number of emitted electrons, rather than simply making each one more energetic. Einstein explained this by proposing that light itself could behave as individual packets of energy. These packets were later called photons. Each photon carried an amount of energy determined by the frequency of the light. Higher frequency light carried more energy per photon. Lower frequency light carried less. If a photon did not have enough energy to free an electron from the metal, then piling up more low-energy photons did not solve the problem in the simple classical way. This was deeply unsettling because light had already been shown to behave like a wave. Thomas Young's double-slit experiment had revealed interference, one of the clearest signatures of wave behaviour. Maxwell's equations had described light beautifully as an electromagnetic wave, yet Einstein's explanation showed that light also behaved like a collection of particles in certain experiments. Nature was now refusing to fit into one classical category. Light could spread and interfere like a wave, but it could also arrive and exchange energy like a particle. It was not merely one or the other, it was something deeper, something that the old words could only partially describe. Atoms brought another crack in the old picture. By the early 20th century, scientists knew that atoms emitted and absorbed light at very specific frequencies. These atomic spectra appeared as sharp lines rather than smooth rainbows. Each chemical element had its own pattern, almost like a barcode written in light. Classical physics struggled to explain this. If electrons moved around inside atoms according to ordinary electromagnetism, they should have been able to emit energy across a continuous range. Worse still, an electron orbiting a positively charged nucleus should radiate energy, lose speed, spiral inward, and collapse into the nucleus. According to that simple classical picture, atoms should not be stable, which is inconvenient given that atoms had taken the trouble to build everything. In 1913, Niels Bohr proposed a new model of the atom. He suggested that electrons could occupy only certain allowed orbits or energy levels. They could jump between these levels by absorbing or emitting specific amounts of energy. This helped explain the line spectrum of hydrogen and offered a new way to understand atomic stability. Bohr's model was not the final version of quantum mechanics. It still used partly classical images, especially the idea of electrons moving in orbit-like paths, but it marked another crucial step away from the old smooth picture. Electrons were not free to have just any energy. Atomic light was not emitted in any casual amount. Nature seemed to prefer allowed states, definite transitions, and discrete exchanges. Planck had shown that energy exchange could be quantized. Einstein had shown that light could behave as photons. Bohr had shown that atoms contained allowed energy levels. Each discovery loosened the grip of classical intuition a little more. These ideas did not yet say directly that a particle could be in two places at once. That stranger conclusion would require matter waves, wave functions, probability amplitudes, and superposition. But the path was now open. The old world of continuous motion and definite little objects had begun to give way to a world of quantum rules. The first cracks in classical certainty were not failures of science, they were successes. Experiments had spoken clearly, and the theory had to change to match them. Physics did not become stranger because scientists wanted it to be strange. It became stranger because careful measurements of heat, light, and atoms showed that reality was already strange, quietly and precisely beneath the surface. Light is one of the oldest mysteries in physics, partly because it feels so familiar. It fills a room, warms a face, glitters on water, and slips through a window without asking permission from the furniture. It seems gentle and ordinary, until we ask what it actually is. Then the calm little beam of sunlight begins to behave like one of nature's more elegant riddles. For a long time, scientists argued over whether light was made of particles or waves. Isaac Newton had favoured a particle-like view, imagining light as tiny corpuscles travelling through space. Later, wave theories became more powerful, especially because they explained effects that particles alone struggle to describe. Waves can spread, waves can bend, waves can overlap, and when waves overlap, they can interfere. Thomas Young's double-slit experiment, first performed in the early 19th century, gave one of the clearest signs that light behaves like a wave. Young allowed light to pass through two narrow openings and fall onto a screen. If light was simply a stream of tiny pellets, one might expect two bright bands behind the two slits. Instead, the screen showed a pattern of alternating bright and dark stripes. That striped pattern is called an interference pattern. It appears when waves from the two openings meet one another. Where the waves arrive in step, crest meeting crest, they reinforce each other and form a bright region. Where they arrive out of step, crest meeting trough, they cancel each other and form a dark region. It is a beautifully simple idea, and also slightly rude to anyone hoping the universe would stay easy. This wave picture became even stronger in the 19th century through the work of James Clerk Maxwell. Maxwell showed that electricity and magnetism are deeply connected, and that changing electric and magnetic fields can travel through space as electromagnetic waves. When he calculated the speed of these waves, it matched the known speed of light. This was a remarkable moment. Light was not just brightness, it was an electromagnetic wave. In this view, visible light is only one small part of a much wider family. Radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays and gamma rays are all forms of electromagnetic radiation. They differ mainly in wavelength and frequency. Radio waves can stretch over meters or even kilometers. Visible light has wavelengths hundreds of nanometers long. Gamma rays can have wavelengths far smaller than atoms. The same underlying phenomenon appears in many different forms, from a cozy infrared heater to a medical X-ray image. By the late 19th century, the wave theory of light looked extremely successful. It explained reflection, refraction, diffraction, interference, and the connection between light and electromagnetism. If the story had ended there, light would have seemed comfortably wave-like. But nature was not finished being awkward. The photoelectric effect revealed a different side of light. When light shines on certain metals, it can knock electrons out of the surface. Classical wave theory suggested that brighter light should deliver more energy, gradually shaking electrons loose. But experiments showed something stranger. If the light's frequency was too low, no electrons were emitted no matter how bright the light became. If the frequency was high enough, electrons appeared almost immediately. In 1905, Albert Einstein explained this by treating light as packets of energy. These packets were later called photons. Each photon carries energy connected to the frequency of the light. Higher frequency light, such as ultraviolet light, carries more energy per photon than lower frequency light, such as red light. A single photon either has enough energy to free an electron from the metal, or it does not. Brightness affects how many photons arrive, but frequency determines the energy of each one. This was a profound shift. Light had behaved like a wave in interference experiments, yet it behaved like a particle when exchanging energy with electrons. It could not be described fully as only one or the other. The old categories were not completely wrong, but they were incomplete. This is the beginning of wave-particle duality. The phrase can sound as though light is sometimes a wave and sometimes a tiny marble, changing costume depending on the experiment. But that picture is too simple. A photon is not really a classical particle, and it is not really an ordinary water wave either. It is a quantum object. In some experiments, its wave-like nature is revealed through interference. In others, its particle-like nature appears through localized energy exchange. This matters because waves can pass through more than one path. A water wave reaching two gaps in a barrier does not politely choose one gap and ignore the other. It spreads through both, and the two emerging waves later combine. When light passes through two slits, the wave description naturally allows both openings to matter. The strange step comes when light is dimmed so much that photons pass through the experiment one at a time. Each photon is detected as a single localized mark on the screen, as if it arrived like a particle. Yet after many photons have arrived, the interference pattern slowly builds up. The pattern suggests that each photon's quantum state was associated with both possible paths before detection. This does not mean a photon is secretly a tiny bead taking one slit, while we are simply unsure which slit it chose. If that were the whole story, the interference pattern would not appear in the same way. The wave-like possibilities have to remain part of the description. They have to combine. Light therefore becomes the doorway into the deeper mystery. It shows that nature can be localized when measured, yet spread out in possibility before measurement. It can arrive as one small detection, while its earlier behavior depends on more than one available route. And once light revealed this strange double nature, the question became unavoidable. Was light special, or could matter itself behave this way too? Could particles with mass, particles like electrons, also act as waves? Could something we think of as a tiny piece of matter also be associated with more than one path? The answer would carry quantum physics much closer to the title's central mystery. Light had already taught physicists that reality was not simply wave or particle. Soon, electrons would teach them that even matter is not as solidly classical as it first appears. For a long time, the wave-like behavior of light seemed strange enough on its own. Light could spread, bend, interfere, and form delicate patterns of brightness and darkness, yet it could also arrive as individual photons delivering energy in packets. That was already a serious challenge to the tidy classical picture. But matter seemed different. Matter had mass. Matter made tables, stones, planets, hands, and laboratory equipment that somehow always ended up slightly more expensive than expected. Matter felt solid. It seemed natural to imagine that matter was made of little particles with definite positions, travelling along definite paths. Electrons, for example, had been discovered by J.J. Thomson in the late 19th century. They carried negative electric charge and had a tiny mass, far smaller than the mass of an atom. In classical terms, it was tempting to picture an electron as a very small charged bead. Perhaps not a bead anyone would want to misplace, but still a bead in spirit. Something with a location. Something that moved through space. Then Louis de Broglie made a bold suggestion. In 1924 he proposed that if light, which had long been understood as a wave, could also behave like particles, then perhaps matter, which had long been understood as particles, could also behave like waves. This was a beautifully symmetrical idea. It did not come from nowhere. Quantum theory had already shown that light had a dual nature. Planck had connected energy with frequency. Einstein had treated light as photons. Bohr had used quantum ideas to explain the allowed energies of electrons in atoms. De Broglie took these clues and asked whether wave-like behavior might belong to all matter. The key idea was that every moving particle has an associated wavelength. This is now called the de Broglie wavelength. The wavelength depends on the particle's momentum, meaning roughly how much motion it carries. A lighter particle, such as an electron, can have a wavelength large enough to matter in atomic experiments. A heavier everyday object has a wavelength so fantastically tiny that its wave nature becomes impossible to notice in ordinary life. This is why you do not diffract noticeably through a doorway. A person walking through a door technically has a de Broglie wavelength, but it's so absurdly small that no doorway, corridor, or patient observer would ever reveal a useful interference.